Alright, so this is our AP Chemistry Chapter 5 lesson video, Part 1, and I'm going to cover Section 5.1 and 5.2. So we're going to jump into thermochemistry, which of course is the study of heat change that occurs in reactions and physical processes. So first we're going to go over a little bit of the background of energy in general, because of course heat is a form of energy. So thermodynamics is the study of energy and its transformations. So we know energy cannot be created or destroyed, but it can turn from one type into another type. Like potential energy can become kinetic energy, which can become heat energy, so forth and so on. So energy is the ability to do work or transfer heat. Work is the energy used to cause an object with mass to move against a force. So reactions can do work. I know that sounds kind of weird. Of course, heat, though, is what we'll usually focus on more when we're talking about chemistry, but heat is the energy used to cause the temperature of an object to increase. So this is just kind of a concept map that I found that relates work and energy and power and how they're all based on thermodynamics. So we're not going to go into this whole thing, but it just kind of shows how they're all related, how chemistry and physics and math, they just all combine into one idea. So first we'll start with kinetic and potential energy. Kinetic energy is the energy of motion. So of course, because atoms, molecules, ions, all the particles that we talk about in chemistry are in constant motion, kinetic energy is a big deal to us. So kinetic energy is 1/2 mv squared, which means 1/2 mass times velocity squared. Potential energy, on the other hand, is the energy that an object possesses due to its position. So gravitational potential energy is mgh, which is mass times acceleration due to gravity times height. So electrostatic potential energy, okay, because a lot of times in chemistry we're not worried about something's height based on gravity, but we'll focus more on charged particles. So electrostatic potential energy becomes more important to us. So our energy equals this equation right here. Now we won't be actually plugging into this equation in this class, but we will use it especially when we're talking about periodic trends. And so this is just a constant, okay, so don't even worry about that. So your Q's, those are the charges. So Q1 and Q2 are a multiple of 1.6 times 10 to the negative 10 coulomb, because remember that's the charge of an electron. So if it's a negative charge, this would be a negative number. If it's a positive charge, it would be a positive number. If it's positive 2, it would be positive 2 times this number. And then D, of course, is your distance. So the important thing to understand is that the energy is based on the charge of the particles and the distance between them. Okay, so like I said, once we get to periodic trends, this equation becomes very important. So like I said, we won't actually be plugging numbers into this equation, so you don't need to memorize this constant or anything like that. But you do need to understand that it's based on charge and it's based on distance. So if Q1 and Q2 have the same charge, then your energy is positive and the charges repel. So we know that like charges repel. And so when you have positive energy, that's considered unfavorable. You want your energy to be negative or as close to 0 as possible. So if Q1 and Q2 have opposite charges, then your energy is negative and the charges attract. So opposite charges attract. And then your energy decreases with increasing distance. So the further apart they are, the lower your energy is, of course, because they can't get that attraction. So chemical energy, of course, we focus on that because we're in chemistry. So chemical energy is due to the potential energy stored in the arrangement of the atoms. So energy is stored within the bonds of molecules. Thermal energy is the energy a substance possesses due to its temperature. Chemical energy and thermal energy are both important in chemical reactions. So see, this is kind of where we're going to focus a lot of our time on in this chapter. So the SI unit for energy is the joule. So a joule is just a kilogram times meter squared per second squared. A calorie is another unit for energy. Of course, that's what we use in America. And so 1 calorie equals 4.184 joules. So you can always convert between the two. And then a capital C, or nutritional calorie. Notice it has a capital C, this has a lowercase c. Is used in the food industry, and it's actually a kilocalorie. So a capital C calorie is 1,000 calories. So if you look at your nutrition facts on your food, it's going to say capital C calories, 200. Well, that's actually 200 kilocalories. So we're actually looking at a much larger number than that. Okay, but don't worry when they tell you you're allowed to have like 2,000 a day. Again, that's kilocalories too. So, system versus surroundings. The system is the part of the universe which we focus our attention on. So that is the reaction itself. It's only the reaction. It is literally the particles that are reacting with each other. The surroundings are anything that is not the system. So this could be the beaker. It could be our hands if we touch the beaker. It could be a solvent. That's kind of weird because you might think, oh, well, the solvent is inside of the flask or the beaker, so how is it, if it's not part of the reaction, it's not part of the system? A thermometer, even if you put it into the reactants, the thermometer is still surroundings, etc. Okay, so our system plus our surroundings equal the universe. So an open system is one in which matter and energy can be exchanged with the surroundings. So if you do a reaction that produces a gas, and let's say it's exothermic, so it gets hot, in a beaker in class, that would be an open system because the gas can escape into the classroom and the heat can be released into the surroundings. A closed system can exchange energy but not matter with its surroundings. So let's say instead you did this reaction in a flask and you put a balloon on the top of it to capture the gas. Well, in this case, now the gas is not allowed to leave, so the matter can't leave. But if it's still just in a flask inside the classroom, it can still release the heat to the surroundings. So that would be an example of a closed system. An isolated system does not exchange energy or matter with the surroundings. So in this case, it would also need to be insulated, so that way the gas can't escape, but the heat can't escape either. Okay, and so there's no perfect isolated system, of course. We can get super close, but you can't always make it perfectly insulated. So, work and heat. Work is energy used to move an object against a force. So work is force times distance. So if the object doesn't move, you did no work on the object, no matter how hard you might have tried. Heat is energy transferred from a hotter object to a colder one. So heat naturally travels from the hotter to the colder object. So, sample exercise. It says, a bowler lifts a 5.4 kilogram or 12-pound bowling ball from ground level to a height of 1.6 meters or 5.2 feet, then drops the ball back to the ground. What happens to the potential energy of the bowling ball as it is raised from the ground? Well, potential energy is mass times gravity times height. So notice it says as it is raised from the ground. Well, if you increase the height, you increase h, then your potential energy is going to increase. So we can say potential energy increases. Now, if they had said because notice it says, then drops the ball back to the ground, as if it had said then, potential energy would decrease. Okay, so as your height increases, your potential energy increases. All right, so next one, it's a little bit of math here. So I already got my answers, that way I'm not stuck using a calculator in front of y'all wasting time. We know these lesson videos are long enough as is. So what quantity of work in joules is used to raise the ball? And then it gave me a note that force is mass times gravity, and gravity is 9.8 meters per second squared. So that's just a constant acceleration due to gravity, 9.8 meters per second squared. But again, most likely you will not be plugging into this formula on the actual AP exam. This is more background information, so, probably not going to show up on the AP exam. All right, so anyway, it says, what is the quantity of work? So we know that work is, of course, force times distance. Let's see. And they told me that force is mass times gravity, and gravity is 9.8 meters per second squared. So the easiest thing to use in this case, of course, would just be our potential energy formula, okay? Because work is, of course, a form of energy. So So if I use my potential energy is mass times gravity times height, then I can just plug in. So my mass, of course, is 5.4 kilograms. My gravity, they told me in my hint, is 9.8 meters per second squared. Even though it probably won't show up on the AP exam, that's just a good number though to kind of know. All right, and then it told me the height. It said it's 1.6 meters. So once I multiply all three numbers, I get 84.67 joules. All right, and so that's what's going on when you raise the ball. That's how much energy the ball has at that point. All right, so let's move on. Oh, there's part C. Okay. I'll write any previous numbers we might have needed up here. After the ball is dropped, it gains kinetic energy. If we assume that all the work done in part B has converted to kinetic energy at the time the ball strikes the ground, what is the speed of the ball at the instant just before it hits the ground? Note, again, gravity is 9.8 meters per second squared. All right, so our energy from part B, because we're going to need that, was 84.67 joules. Okay, so it says all of that is converted into kinetic energy. All right, it tells me that in the problem. All right, so we have our kinetic energy. So our kinetic energy wait, what is it asking? What's the speed? Okay, so our kinetic energy formula is 1/2 mass velocity squared. So I need to solve for velocity. So since I'm dividing by 2, because it's a half, I'm going to multiply both sides by 2 to get rid of that half. I'm going to divide both sides by mass to get rid of that m. But the problem is that leaves me with v squared equals 2 kinetic energy over m. So you do have to get rid of the squared by square rooting both sides. So that gives me velocity is the square root of 2 times kinetic energy over mass. So I just plug in. So 2 times my kinetic energy was 84.67 joules. And, whoop, I forgot what the mass was. Let's see, I have it written down. The mass was 5.4 kilograms. That was given in the initial part of the question on the previous slide. All right, so once I solve, I get about 5.6 meters per second. Just like that. All right, so again, most likely you will not be plugging into these formulas on the AP exam. 1, it's too easy, but 2, it's just not super related to chemistry. Obviously, we're not going to be dealing with bowling balls and things like that. But still, it's good practice. You should always know how to plug into formulas. All right, so maybe you try these, pause the video, try them yourself, or if you want to watch me do part A and then you try part B, that would be fine also. All right, so I'll assume you've already done that. Get my marker ready. All right, so it says, what is the kinetic energy in joules of an argon atom moving with a speed of 650 meters per second? And then it tells me 1 AMU is 1.66 times 10 to the negative 24 grams. So one important thing to note is that when you use the kinetic energy or potential energy formula, your mass must be in kilograms. Obviously, if we're talking about one atom of argon, we don't know the kilograms off the top of our head, so we're going to have to, convert that. All right, so we know kinetic energy is 1/2 mass times velocity squared. So see, they gave me velocity, 650 meters per second, so that's great. I can use that. But the problem is the mass. I need the mass in kilograms. So if I look at the periodic table, argon is about 40, it looks like. So let's start with 40 AMU. All right, it tells me in the question that 1 AMU is 1.66 times 10 to the negative 24 grams. Okay, so I can get rid of AMU. But I got to get to kilograms. So I know that 1 kilogram is 1,000 grams. So then my grams cancel. So now I got to kilograms. So once I solve, I end up getting 6.64 times 10 to the negative 26 kilograms. Okay, and as always, there's more than one way you could have gotten to that number. All right, that's the way math works. There's always more than one way. All right, so now we're ready to plug in. So my kinetic energy is 1/2 times my mass, which I just calculated, 6.64 times 10 to the negative 26, times my velocity, but don't forget to square it, okay, which was, it's in the question, 650 meters per second. I need to square that. Now, the important thing you have to remember is when you put this into the calculator, if you just do half or 0.5 times this, and then square, sometimes it'll square the whole thing. So make sure you're only squaring the 650. All right, so once you do all that, you should get 1.40 times 10 to the negative 20 joules. So hopefully you got that. All right, then part B says a mole of argon atoms moving with a speed of 650 meters per second. Okay, so this is the energy of one argon atom. So now it's asking me for a mole of argon atoms. So hopefully you remember that 1 mole is 6.02 times 10 to the 23 representative particles. So in this case, the representative particle would be would be atoms, because we're talking about argon, which is a noble gas. All right, so the first thing we need is, of course, the mass of 1 mole of argon atom. All right, so we know that 40 grams can become kilograms by saying that 1 kilogram is 1,000 grams. Because, of course, when we're talking about a mole of a substance, we can use the number off the periodic table, but we can put grams behind it instead of AMU. All right, so that turns it into 0.04 kilograms. All right, and then we just plug into our kinetic energy formula. 1/2 my mass, this time my mass is 0.4 kilograms, times my velocity squared, 650 meters per second squared. And then I just multiply it, and I get about 8,450 joules. Okay? Now, of course, you could have done this a different way. You could have started with this number and then used your Avogadro's number to convert, which is fine. I just wanted to show you using the formula again, just so you get comfortable using that formula. Okay, but remember, in math, there's always more than one way to do something. All right, so hopefully you got one of those right, or both of them right. Whoop, my clicker has died. What the heck? Okay, well, this could get interesting. I don't know what's wrong with it. All right, so section 2, the first law of thermodynamics. So the first law of thermodynamics states that energy is conserved, so it can't be created or destroyed in any physical or chemical process. However, it can turn into other forms of energy. So energy can transform from one form to another and can move to different places, but the overall energy must remain constant. Oh, great. Guess I'll be clicking like this today. See if it's... Nope, okay. All right, so the internal energy, or E, of a system is the sum of all the kinetic and potential energy and all of its components. So calculating energy by itself is difficult, but calculating the change in energy is easier and more useful. So whenever you see delta in science or in math, it means change in. So it's always final minus initial. So delta E is your final energy minus your initial energy. So if delta E is positive, then the system has gained energy. If delta E is negative, then the system has lost energy. So delta E equals Q plus W. So Q is heat and W is work. When heat is added to a system or work is done on a system, its internal energy increases. Okay, so you have to be careful on these questions to make sure you read to determine if it's being added to or taken away from the system. All right, so oh my gosh, this is a super long question, but the answer is super short. So it says 2 gases, A and B, are combined in a cylinder and piston arrangement like that in figure 5.3. Substances A and B react to form a solid product. So A plus B gas makes C, which is a solid. As the reaction occurs, the system loses 1,150 joules of heat to the surroundings. The piston moves downward as the gases react to form a solid. As the volume of the gas decreases under the constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. What is the change in internal energy of the system. Okay, so we know E equals Q plus W. So we just need to determine the signs of Q and W. Like all this other stuff, this is just extra information. So it says it loses 1,150 joules of heat. That means that heat is negative. Okay, so for Q, I'm going to put in negative 1,150 joules. Okay, so you got to be careful in the reading. And then it says the surroundings do 480 joules of work on the system. If work is done on the system, that number is positive. So 480 joules. Okay, so once I combine these two numbers, I get negative 670 joules. So see, all that wording just for a super simple answer. All right, so I'll let you try the next one. And hopefully, for my next video, I can get my clicker fixed. I think the battery might have died. Oh well, we'll figure it out. All right, so you tried this one. I'll assume you've done that. So it says calculate the change in the internal energy of the system for a process in which the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. Okay, so remember, we know E is Q plus W. So let's look at our sign for Q. So it says it absorbs 140 joules of heat, so that's going to keep that number positive. All right, and then this time it says the system does 85 joules of work on the surroundings. So when the surroundings do work on the system, we count that work as positive. When the system does work on the surroundings, we count that number as negative. So that would be negative 85 joules, and when I combine my two numbers, I end up with 55 joules. All right, so hopefully you got that one right. This is pretty easy. Like I said, the main thing is just figuring out the correct sign. All right, so next is endothermic versus exothermic. So endothermic is a process which absorbs heat from the surroundings. So your Q would be positive, and exothermic is a process which the system loses heat to the surroundings. So your Q would be negative. And the important thing to remember is it's based on the system, not the surroundings, and your hands are the surroundings. So when you touch an endothermic reaction, it is absorbing heat from the surroundings. So if it's absorbing heat from your hand's going to feel cold. So endothermic feels cold to us. Exothermic, if you touch the beaker of an exothermic reaction, it's losing heat to the surroundings. So if heat is going into your hand, it's going to feel hot to you. All right, and last thing is a state function. So a state function is a property of a system that is determined by the system's present state and not affected by the path taken to get there. So delta E is a state function. So for example, 50 grams of hot water cooling to 25 degrees Celsius versus 50 grams of ice warming to 25 degrees Celsius. It doesn't matter that this first one had to cool down to get to 25 degrees and the second one had to warm up to get to 25 degrees. What matters is at the end, they are both 25 degrees Celsius. Another way to look at it is in this parking garage. There's an elevator to lift your car up to the 4th floor, or there's a ramp where you can go up every single floor yourself. It doesn't matter that they took two different approaches to get to the top. All that matters is they both ended up at the top. That's what a state function is. All right, so sorry about the issue I was having with my clicker today. Hopefully I'll get that fixed by the next video, and hopefully all this background information wasn't too confusing. Remember, it is just background information, so most of this content probably will not be directly addressed on the AP exam.